All right, hello everyone. So today we have a Calculus 3 problem, multivariable calculus problem, where we have find the potential function f that goes from R3 to R such that the gradient of f equals capital F. It's a vector valued function where capital F is made up of three components: 2xy, comma y cubed plus x squared, comma e to the z. So please recall what it means to find the gradient of a scalar valued function. It basically stands for making a vector valued function for which each of the components of your vector valued function are equal to the partial derivatives of the scalar valued function. So it's equal to fx, comma fy, comma fz, or partial f with respect to x, partial f with respect to y, partial f with respect to z. All right, so if we take what this, with the idea of a gradient, what that means, and I set it equal to f because that's what we're saying is capital F, so gradient of little f equals capital F, then I must have that these two vector value functions equal each other. So I must have that the partials must equal each other. So for example, fx must equal 2xy, fy must equal y cubed plus x squared, and then fz equals e to the z. Okay, so from there we can get f somewhat, it's a little straightforward, not easy necessarily, but straightforward. So here's what I would do to find f. I would take any one of those three parts, doesn't matter which one, and I would integrate with respect to whatever the partial derivative that was given. So for example, if you take f x, 2xy, and you integrated that with respect to x, you would get what your function f would look like its basic structure. So if I integrated fx, the 2xy with respect to x, you get x back because 2xy equals fx. You would get x squared y, because remember, y is a constant here, plus, okay, and speaking of constants, when you go back to your Calc 1 class, you always added a constant when you're taking an antiderivative or finding an antiderivative. Well, similar here, but instead of a constant, you have a whole function, and it's a function that's made out of the two other variables that you have that you're working with. So in this case, what I mean by that is I'm going to have a function that's made out of y and z. Okay. And the reason for that is because we're taking the derivative with respect to x. Anything that does not have an x in it, when you take its derivative, would go to 0, it would go away. So that's why we add that on. More explicitly here is if I had let me replace g of yz with an explicit function like y cubed z to the 9th. So I'm claiming that my function f has this structure going on. The reason for that is because, if you took the partial derivative with respect to x of this, you would get fx equals just 2xy, and then the y cubed z to the 9th part goes to 0. So that y cubed z 9 part represents, again, what g of y z might look like. And my big point here is just to show you that the partial derivative with respect to x of all that would just go to 0, because you just have y's and z's there. Okay, so that is what my function would look like, and your task here is to find what g of yz is equal to. And the way we do that is by considering the other parts of that we're given. We're given that fy equals y cubed plus x squared, and fz equals fz. So the way this works is that you're going to take f partial y of the function we have right now, the x squared y plus g of yz. So again, you find your f, your potential f function here, then you take the partial derivative of the other, one of the other variables you didn't work with. So with respect to y, and you would get x squared plus partial g partial y, and you would set that equal to what fy is supposed to be, which is y cubed plus x squared, and you make up an equation. And if you solve this equation, you would get change in f, change in y equals y cubed. And likewise, to get f, I would change in g, excuse me, change in y, I apologize. And if I wanted to get g, I would integrate dy here, respect to y, And yeah, if you notice change in g change in y is just equal to y cubed, what that means is that the y part and the z part are standalone. They're from each other in the sense of, like, you take the y part plus the z part. So if you integrate y to the third, you would get y to the fourth over 4 plus some constant, but in our case, our function constant is some function, and it's in terms of z. Okay, so again, that is what my function g would have to look like after you integrate. Okay? And this often will happen. You have this partial derivative with respect to whatever variable, you integrate it, and you're adding a function to it of one variable. That's what's left. And last but not least, and we'll get to that in a second, let me write what f looks like at the moment. So f was equal to x squared y plus g of yz, which is x squared y plus y to the fourth over 4 plus h of z. And your task here now is to find what h of z is. Okay. Now, this is long-winded. I'm not going to lie to you. But to me, this is the actual, not maybe the it's a little more straightforward way to do this. There are other ways of doing this where you match up partial derivatives and such, but to me, it's that some confusion with that. And that basically would involve, like, integrating each of your partial derivatives and then matching things up. But anyways, I'm not going to get into that. So fz here, I'm going to take the partial derivative with respect to z next, because I worked with y. And that's got to equal my partial derivative with respect to z of what I'm claiming the gradient is equal to, which is e to the z. And yeah, if you found your h here, that would equal e to the z plus now just some constant, because, yeah, h prime of z, h of z is just one variable function now. And therefore f, or f of x, y, and z, if you put everything together, would be x squared y plus y to the fourth over 4 plus e to the z plus constant c. Okay? All right, so that's how this method works. So again, you would set each of your, basically your partial derivatives equal to the components of the vector field given, and you choose any one of these. Doesn't matter fx, fy, or z. Whichever you pick, you're going to integrate respect to whatever the variable integration. So I picked fx, 2xy, integrated with respect to x, and you always get the antiderivative of that plus a function that's in terms of the two other variables. And your task is to find that function of two other variables. What you do is you take now the partial derivative of those two other variables, y or z. It doesn't matter which one you start off with. And you take that partial derivative, and it involves some function plus some partial derivative expression, change in g, change in y, or change in g, change in z, whatever. And you set it equal to what the partial derivative of y was supposed to be from the given vector valued function, excuse me. So y cubed plus x squared, and you have an equation here, change in g, change in y, you integrate it, and yeah, you go ahead and figure out what the structure of g looks like, and then finally you go ahead and take one more derivative to figure out what this h of z function would look like. And once you have all that, you put all that together, and there you go. And of course, you can check this by taking a partial derivative with respect to x, y, and z, and it should come out to be what you have there. Okay, so I know this was a longer video, so thank you for your patience, and I hope this helps. Thank you for your time.